Python Shellcode Execution Redux. Here we go. I've talked about Python Shellcode Execution before, and I'm going to talk about it again. If you don't know me, here's the perfunctory About Me slide. I'm a security analyst, researcher, pen tester with Black Hills Information Security. I have been with Black Hills since 2013 when we were, get this, 4 people. Okay, we're somewhat bigger than that now. I'm also an instructor for Antisyphon. I have a regular expressions class out there, which is a nice little 4-hour on-demand class that you can get. And I have an introduction to Python class as well, which you are absolutely welcome to take either on demand or at one of my live virtual or even live in person. I do make some appearances in various places. All right, so here's the scenario, and this comes up quite a lot for people these days because Python and Windows actually go together quite well these days. So you're performing an internal pen test. Woohoo! You managed to compromise some sort of Windows application server via whatever it is, credential acquisition, maybe you used Responder, maybe you used Mimikatz, maybe SMB relaying or DC sync or something. You got some credentials you can get onto a Windows application server. So you go for the obvious, which a lot of us do. It's like, hey, I bet you I can just RDP, use remote desktop protocol and just log into that server with these brand new credentials. Now, as the elite pen tester that you are, you would love to get some sort of C2 channel from that server back to your favorite backend C2 framework. Maybe it's Cobalt Strike, maybe it's, God forbid, even Metasploit or Mythic or whatever framework that you've got an interest in using. You notice pretty quickly, because you're poking around the server, doing a little basic recon as we would do, that it has, application whitelisting. It's got 365 Defender. Maybe it's got a EDR or XDR layered on top of that. And, you're feeling like, I'm not going to be able to drop a DLL, or I'm not going to be able to drop an XE or a Visual Basic app or whatever on this box. It's probably going to fire some kind of alarm, an alert, and I'm going to get caught. But in your exploration, you found a Python 3 interpreter. Now, your life is good right now because a Python 3 interpreter allows you to run code. Or alternatively, maybe it's a more desktop style machine, you fire up the Microsoft App Store and you install a Python 3 interpreter. That's cool. It happens. Let me tell you, it does happen. So it would be nice to use that Python interpreter to get some shellcode into memory, such as your Cobalt Strike shellcode or whatever other framework of choice, and get it running so that you can establish your C2 channel. Well, what is shellcode? Just a refresher, right? Well, shellcode is just compiled machine code, right? It must be position independent. What does that mean? Well, that means when that shellcode, or machine code if you like, runs, it cannot have any dependencies on other data sections. It can't have a heap dependency on some sort of variable existing at a certain memory location. Everything must happen actually in the stack as you run that machine code. That's what we call position independent shellcode or position independent machine code. Now, the machine code is going to have some kind of architecture or flavor to it. It could be x86, 32-bit machine code, or it could be x64, 64-bit machine code. More than likely today, you're going to be operating in a 64-bit world because, well, frankly, there are fewer and fewer 32-bit machines out there these days. But don't actually rule out 32-bit entirely. We were just chatting on pre-show banter earlier about how you might find, something like an embedded Windows NT kernel running in a scanning electron microscope from 1998 or something. There are situations where you will run into an old 32-bit scenario, right? The point is the shellcode has to be OS platform specific. It has to match that machine architecture. Shellcode is often not the same as an exe or a Linux-L file. It cannot be directly loaded from the operating system. It doesn't have a structure to it like a PE common object file format structure, right? And it can originate from almost anywhere, right? Metasploit, Cobalt Strike, found online, handcrafted even. I've handcrafted a few shellcode samples in my days. Well, okay, there's the point. We've defined what shellcode is. Now let's talk about Python for a minute. Python 3 has a special module built into it called the ctypes module. What does that mean? Well, ctypes is a foreign function library for Python. It actually provides the, really, Microsoft in the Windows context, Microsoft foundational C compatible data types, and allows us to call functions in DLLs or shared libraries. Aha. Well, if this is the case, and you want to execute shellcode and get it into memory, then ctypes seems like the avenue that you need. In fact, ctypes exports a structure called CDLL, and on Windows, WinDLL and OLE DLL objects for loading, direct loading of dynamic lib libraries. Cool. So this is something that a lot of people don't know about, but it's really, well, let's just say it's really handy, right? Now, how would you know about that? Well, this is the RTFM thing, right? Hey, hold my beer. I'm going to go out and read the documentation. Highly overrated, I know. You get an RFC or a piece of lengthy documentation. If you take it to bed and read it, you're going to go to sleep pretty quickly. But sometimes you actually have to read the manual because when you do read the manual, you find out things. Amazing how that works, right? ctypes has this WinDLL object, and using WinDLL.kernel32, we can actually extract function pointers for any kernel32 DLL API call that we need. Aha! This is critical because in Windows, we need to use the kernel32 API, well, to do things like allocate memory and stick position independent machine code into that memory to execute shellcode, right? And in fact, we can import ctypes into the Python interpreter. We can define a pointer to a kernel32 API call using ctypes.windll.kernel32.createThread, for example. CreateThread is a kernel32 API function call. And it will tell you that the type of that object is a ctypes.cdll.init, locals, et cetera, It's a function pointer. It is a call that you can use to actually execute the kernel32 API function create thread in this instance. That's handy. All right, just a quick refresher. Windows architecture, all right? Kernel32 is well documented on MSDN. Anytime you need to use any of the Windows API itself, most of those function calls exist in kernel32.dll, and now it's related kernel-base.dll. Underneath that DLL, there is another runtime library called NTDLL. Now, NTDLL is kind of a translation layer between what we call user mode code and the kernel, the Windows kernel that's running underneath. NTDLL, while you can use API function calls from NTDLL, they are not publicly documented. NTDLL is something that Windows, or Microsoft, sorry, reserves the right to change the internal implementation of from release to release of Windows, and in fact, they do. So if you do code up something with NTDLL in mind, it might change on you, even if you search the internet for the undocumented functions for somebody else that's documented them, right? And there are places where you can find that, and then you code it up. You might actually have the rug pulled from under you. Kernel32, however, is a consistent API interface that's always going to be there. Now, the next thing we got to ask ourselves, in Python, how do we pass function call arguments to the Windows API function, a kernel 32 API function? Well, we have a bit of a translation problem. We have something called Python objects, and we have something called C object types. And these two things aren't exactly the same. But there is a translation table, if you like. The Python object none actually maps over to the C type object of null. The Python object of integer will map over to the C type of int, and so on. So you can translate between these two things. When you need to make a kernel 32 API call, you need to use the C type, the C data type, because that's what that API is written using. It was written in C many, many years ago with the release of the original Windows NT kernel. To help out with this, the Python C types module defines a number of compatible C types already for you, and you can use these as functions to create a compatible type. Here's a table of them out of the C types documentation. There is a C underscore bool type, for example, right? The Python mapping type is bool, or just bool, right, for Boolean. There is a C types module called C underscore char, C underscore wide char, which is a 16-bit Unicode little endian string character, and so forth, right? So you've got all these extra helper functions in C types that helps you get your data into the right format. Now, if you don't do this correctly, it's very easy to crash your Python interpreter process when you're calling C functions from the kernel 32 DLL, or any other DLL for that matter, but most often it's going to be the kernel 32 DLL. So specifying the argument types is a good defensive practice for code stability. It actually helps us protect against incompatible argument types, is very similar to the idea of function prototyping in the C programming language directly, and that's really not a surprise because these are, in fact, function calls to C libraries in the Windows kernel. There is an arg types attribute of any C function pointer object that we can use to construct these data prototypes for the API calls that we're interested in using. There's also a res type attribute that allows us to specify the function return type. Otherwise, it will actually default to int. Now, if you're interested in another source of the mapping of the various Windows data types, for those that don't know, the Windows kernel has a well-defined historical data typing that maps over to C data types, which in turn maps over to things like C# or managed code data types. You can go find plenty of tables online. This is one of them, where we have the Win API, or the Windows defined data types, on the far left here, and then we have the C type and then the C# or managed type in the middle. And you can get a sense of what those various things are. It turns out that the C types module also has a Win types module, which is really a subdirectory of the module, that you can use as well. So the Win types, it can be very, very helpful. It's not necessarily comprehensive, but it has a lot of the Windows data types if we need to use them. And in fact, I do use them in the shellcode functions that I'm going to come up with. So that was all background. Putting all this together, if we wanted to define a Windows API function call to create thread. Now, create thread, for those that might not have as much familiarity with the Windows operating system, every Windows process is really just kind of like a container full of threads. It's a container that manages the different threads of that process. And create thread enables you to create a new thread in that container of the current process. So if we wanted to define a Python function to call create thread in kernel 32, you can do it like this. You define the function pointer first, create thread equals ctypes.windll.kernel32.create thread. Then we set up the argument types using the appropriate either win types or C types if the win type is not there for the various arguments that the function expects. Now, how do you know what they are? This is where you have to go to the documentation. You go search for MSDN and search for the create thread function, and it will tell you in standard Windows types what the argument types need to be, okay? And you have to do a little research there. There's also another well-known library of things called Platform Invoke or P-Invoke, where you can search for this information as well. So now we can define a function prototype to call create thread in Python. Now let's zoom forward, excuse me, to the idea of executing shellcode in Python and the Windows API, right? There are many techniques that we can consider when we execute shellcode, right? Remote process, let me try that again. Remote process injection is something that people have used in the past, still use in the present, but it is in fact quite dangerous in the world of EDR and XDR because the combination of kernel callbacks and event tracing for Windows acts as an instrumentation source for the EDR and XDRs, and a remote process injection is going to be quite easily detected these days by EDRs and XDRs. Now, there's ways around that. I'm not going to talk about some of the evasion techniques today. I'm going to talk about this in the Python context. If you create a thread in the same process, you're normally a little bit safer, and the typical sequence is to allocate some memory, copy the shellcode into that allocated memory, then create a thread with the starting address of the allocated memory, and then just wait on that thread forever or until it terminates, right? We may need some code, depending on how the shellcode is constructed, to keep the Python process alive so our shellcode execution will continue. That's kind of context dependent. Most shellcode, if it's a C2 channel, is going to block, and that wait on the thread forever part of the API call will stop us from having to write any other arbitrary code to keep that Python process alive. Here is an example of how to do this in Python. Now, this is done in an object-oriented Python class in the sample scripts that, wait for it, I'm going to give you, okay? This is something called SCE_same process. My SCE notation stands for shellcode execution in the same process. And here is how we do it in Python. We've already defined, we're going to assume away that we've already defined our function prototypes. You do have to do that, but we've already defined them. So we're going to allocate some memory using the API called virtual alloc, and we're going to initially allocate that memory as page read write, which means it's not executable. And we're doing that deliberately because we don't want the defenses on that machine to see that we just allocated executable memory. We want them to be blind for a little bit longer. Then we're going to use the function called RTL move memory to copy our shellcode into that allocated memory. Okay. Then we're going to use a function call in kernel 32 called virtual protect, which changes the protections of that allocated memory from page read write to page read execute. Notice that I deliberately left write off. Now, there's another aspect of this. If you ever set a virtual memory page in Windows to read, write, and execute, the EDR industry will stomp on that process immediately. That is a glaring red flag, and it is something you ought not do unless you just want to get busted, right? All right, so there's that. That's why we did this in 2 steps. Then we create the thread pointing at that shellcode, and then we wait for that thread object using the wait for single object, and we wait infinitely. We're blocking and waiting for as long as we possibly can. That's a 32-bit value at 4 million or so. It's the very largest 32-bit value we can wait on, okay? And we've created a shellcode thread, right, inside of a Python process, which is, well, kind of awesome, right? All right. Now, there's another aspect, by the way, on the EDR defenses. If you create today, if you create a memory page that is not backed by some loaded mapped DLL in that process, the EDR is probably going to catch you. So it's entirely possible or probable from an EDR perspective that you're going to get caught even with this code as well written as it is. I'm so humble, right? Yeah. All right. So let's jump forward. Machine architecture, of course, matters. If you're creating a local thread in Python 3 and the Python 3 process is 64-bit, then the shellcode itself must be 64-bit, okay? How do I know if Python 3 is 64 or 32-bit process? Well, there's a couple of different ways. You can import sys and check the sys.max size variable, and if it is equal to 2 to the power of 32 minus 1 or 2 to the power of 63 minus 1. That will tell you whether you have a 64-bit or a 32-bit processor. But, sorry, Python interpreter. But you could have looked at the banner of the Python interpreter as well and probably seen that it was 64-bit. There's another module in Python called platform that you can import, and you can call platform.architecture, and it will tell you whether it's a 64 or 32-bit machine, right? Now, if you are creating a thread in a remote process, you must match the architecture of your shellcode to that remote process architecture. It is possible, although somewhat tricky to code, to inject from a 32-bit process into a 64-bit process. But let's just not go there. That gets into a more complex scenario. The myriad of ways that EDR and XDR can bust you are many these days, right? You might get a sandbox execution environment whereby pre-execution, it takes that process, it replicates it, it puts it in a sandbox somewhere, and it tries to execute it. You can easily write in code to check the time zone, that is, if it's UTC or the number of CPU cores is less than, let's say, 2 or 3, and then exit the process. You can basically evade sandbox execution. The other one that's interesting is if the entropy score on the artifact that you're generating is too high. That's often more applicable to compiled artifacts such as DLLs or binaries than it is to Python scripts, right? Python scripts, the entropy is probably going to be lower by default, but you can lower the entropy artificially by putting in things like lots of nulls or lots of English words to evade this possibility. I already mentioned if you allocated read, write, execute virtual memory in a remote process or even the local process, the EDR is probably going to kill that process immediately. Specific API call hooking in anti-DLL in user mode. You can certainly try to use direct kernel calls using tools like syswhispers, so on. That's more C language applicable. API call hooking is something that was very, very popular a few years back. A little less popular now in that EDRs are tending to lean more towards event tracing and kernel notifications, the kernel notifications being things like image load, process start, thread start, things like that. Right? Static analysis match on shellcode, definitely a problem. Use some sort of encoding or encryption. You can evade that normally. And then that final one that I mentioned is memory scanners looking for virtual memory that's not backed by a disk image. That can get you into trouble as well. Now, there's a way to evade that. I don't have that in this particular code, but you can play a trick where you can make the thread base address look more legitimate when you create the thread. And then what you do is you suspend the thread, and then you switch the base address to your actual shellcode, and then restart the thread. And basically, you're fooling the EDR to thinking that you created a legitimate thread out of some legitimate DLL, and then you're pulling the rug out from under it and switching that base address after suspending and resuming the thread. That's kind of a fun trick as well. Okay. Signature matching, obviously well-known shellcode has specific pattern of bytes, can easily fire a rule on static artifact analysis. High entropy will fire a rule. Another thing that's pretty well known is that Cobalt Strike leaves an easily detectable profile data directly on the process heap. That's an IOC that gets detected a lot. So, at minimum, we need to encrypt or encode our shellcode in the static artifact. If you're more advanced and you have a shellcode ability to modify shellcode, what's going on today more often is that we have dynamic encryption of heap artifacts at runtime during any of the sleep intervals of the C2 shellcode. That's a more sophisticated technique. For encrypting and encoding the shellcode, symmetric encryption is the easiest way to evade static artifact matching. Of course, you're going to have to retrieve the encryption key somehow in that artifact so that you can actually decrypt the shellcode before executing it, right? Easiest way is just to stick it in the same script if it's a Python script, or have it retrievable across the network somehow. I've played with the idea of having encryption keys just sitting in DNS records that you can just go look up when the artifact fires. There's all kinds of choices here. You might want to use AES, Blowfish, RC4, some symmetric cipher. The negative impact to encryption, though, is the entropy of the artifact will increase because you have a lot of static encrypted data with same byte frequency over a very large amount of data. That's going to raise up your entropy when the entropy analysis occurs. And any entropy analysis over a score of about 5 or 6, if you use like the ENT command on Linux, is going to fire a match with most EDRs. So you need to keep that entropy low. But here's an interesting twist for you. You could think of using a Caesar cipher-like approach for shellcode. And I've done this in a number of different areas. Instead of using some form of encryption, why don't we just use a language dictionary, the English language, for example, to represent bytes? And so you could have a single English word represents a single byte value. You only need 256 English words, right? I mean, 255 actually, right? So it's kind of like an encoder to encode your shellcode into English words. And if you do this, you actually lower the entropy as in the same breath because you're not using this encrypted data. You're actually just using English words. Your artifact gets a lot larger, and it's kind of a cool, fun thing to do. So I'm going to show you some of that technique as well in a little bit. The simplest encryption that you can use is just exclusive OR. The mathematical exclusive OR function can be used for symmetric encryption because we call the exclusive OR function a bit flipper. You take a character, you convert it to a byte, you XOR it with the key byte, and you get, well, cipher byte, if you like. Now, if you take that cipher byte and you XOR it back with that key byte, you recover the original plain text byte. So on a single byte basis, exclusive OR works very, very well, okay? And you can even make it a string of bytes that rotate, with a modulus with XOR as well. So you can go a little bit further. If you're XORing multiple bytes, one of the nice things in Python, this is an optional thing, at least for your encoding stuff, you could use the NumPy module, which is a high-performance scientific computing package. And using NumPy, we can perform byte array XOR operations very, very quickly. Now, for your shellcode artifact that you deliver into the target, though, you don't want to use NumPy because NumPy is a third-party module that you want to install. So your decryption would have to use just traditional Python mathematical operations. So here's some encryption script snippet stuff where I'm just XOR encoding some bytes by a single integer and using actually NumPy to do the bitwise XOR of the data and returning back the encrypted result. So nothing too amazing there. It's just a little snippet of code that performs shellcode encryption. Okay. For English word encoding, it's a little bit more fun. For English word encoding, you want to write some code that goes ahead and just reads in an English dictionary and picks random words from the English dictionary until it's got 255 total words. And that's going to be your Caesar cipher entity. And of course, they need to be 255 unique words. Then you need some sort of function, which I've called process shellcode here, that just opens the shellcode file, reads through, and byte by byte substitutes each byte value for one of the English words in the artifact. And then you end up getting this giant list in Python of just English words representing your shellcode. So in my scripts, with these two encryption and encoding methods in mind, I wrote two shellcode execution scripts. One's called pyshellcode1.py, which is an XOR-based encryption, and the other one is called pyshellcode2.py, which is an English word dictionary-based shellcode encryption. And using some Python import syntax, I can easily import the encoded artifacts into these shellcode execution scripts, which I'll show you here at demo time, right? What about process injection? Should we try to inject a process with shellcode? Well, why not? We can certainly try, and we can write code to do that in Python as well. So there's lots of different potential techniques for process injection. In our case, we're going to stay old school. When I'm talking about like original, traditional process injection that's been around for quite some time. And it's likely going to get you busted, but we're doing this for educational purposes, right? So here's the methodology we need for process injection. We need to open a process with appropriate rights. And it's got to be a process that you have a security token to actually open, right? It's probably a process that's running under your same user or a lower mandatory level on the system. Then we need to allocate virtual memory in that process. Then we need to copy our position-independent machine code or our shell code to that new memory in that remote or foreign process, and then tell the remote process to create a new thread. That's what process injection is. Nothing more amazing than that, right? Now, naturally, the question is, what process would we want to target for a process injection? Well, again, the fun part here is we can actually write a function to find one. Now, this is going to require a third-party package as well, so just be aware of that. But there is a Python package out there, which I actually talked about in my last webcast, called psutil. That's very, very handy. And psutil is a process utility package that is very, very well written, and it's actually cross-platform. But we're going to talk about it here in the Windows context. So I wrote a Python method here to find a target process, and it has an optional parameter called preferred here to target a specific named process. And I just went after svc host.exe, but you don't have to do that. You could go after runtime broker.exe or security GUI UI.exe or whatever. You can go over after a number of these things. Anyway, this find process code actually tries to do things relatively intelligently. It goes through all of the process IDs in the system, and it tries to see if we own the process first. So let's try to fetch the name of the process and the user of the process. Well, if we don't have adequate process rights to fetch that, we're going to execute the code block continue to just go on to the next PID, because we probably don't have a security token if we cannot fetch the process name. Next in our loop, we're looking to see if the process name, the username, sorry, is the same as our own username, and the process name is one of our preferred processes that we're trying to inject. If those two things match, we're going to add that PID, the process identifier, to a candidate list. This is a process that looks like we might want to use it. And the reason we add it to a candidate list is once we come out of that loop, in the bottom part of this function, we actually make a random choice of these candidates to return back to the main part of the program. So what that means is that if I go after, let's say, service host.exe, I'm not targeting the exact same PID every time I try to find a process. And that's kind of fun because it shuffles it up a little bit. Being unpredictable is the name of the game when you're in the hacking world, right? You've got to be unpredictable. The sequence of API calls that you need is as follows, and this is all kernel 32 stuff. You need to open the process that you're targeting. You need to allocate memory in that process. This time we use a function call called virtualloc.ex. We need to write to that process memory using the write process memory API call. We need to reprotect that memory with virtualprotect.ex back to read execute. And then we need to use create remote thread to create the foreign process thread, and then we close the process handle. That's the right way to get that thread executing in that foreign process. Hey, look, it's demo time. Sweet. Let's do a little bit of demoing. I'm going to share a different window really quick here. And this is a Windows virtual machine called Demo. Okay. Hopefully everybody can see this. And on this Windows virtual machine, I'm going to start up a Windows terminal. Okay. And hopefully this Windows terminal starts up anytime now. PowerShell. Okay. This is PowerShell 7 in Windows 10. This machine is running standard Windows Defender. And I'm going to set my directory default into a Git repo called Python Shellcode Redux. Okay. And there's a number of Python scripts in here, and I want to point out what these scripts do. Okay. Also, there is a shellcode directory in here, right? Firstly, in that shellcode directory, there is straight out of the Metasploit project a shellcode to execute the notepad 64-bit and a shellcode to execute the notepad in 32-bit. Okay. And they were generated using MSF Venom. And it's this MSF Venom, MSF Venom syntax that was used, right? You probably be familiar with this, right? That's the kind of command I use to generate the shellcode. All right. Now, MSF Venom's not on this system. I just wanted to kind of point that out. All right. Now, once I've generated that shellcode, I have a couple of helper scripts here. One of them is called XOR encrypt. And XOR encrypt allows us to feed some raw shellcode, and it will output a array that you can use in a Python script to then encrypt that shellcode. Now, I'm going to actually go into VI here and just show you this. Oops, try Vim, XOR encrypt, okay? And you can see this is a fairly simple Python script, and I showed it earlier. And its job is to write data to an output file from that shellcode. So let me show you how this works. I'm just going to copy from the shellcode notepad.bin, and I'm going to call this joff.bin for a minute. And then I'm going to run the XOR encrypt, right? And I'm going to, with that XOR encrypt, feed it the file joff.bin, okay? And I'm going to use an XOR key of the number 23. And this is arbitrary. It's just a number between 0 and 255. Well, it was actually 1 and 255 because 0 means don't encrypt in this case. And I'm going to run it, and it writes a file called joffelncrypted.py. And if we look at joffelncrypted.py, I keep typing VI, sorry, you'll see that it's a Python byte array that it represents the encrypted shellcode, right? Nothing too amazing here, right? So that's that example. Now, the words encode script does something a little bit different, okay? It allows you to, again, provide it with shellcode and a word dictionary. So I've got a word lists directory here, and I'm going to use English Common, okay? And I'm going to give an output file of joff.py and provide it joff.bin. Right? And we'll let it do its thing. All right. Live demos are always fraught with danger. You do know this, right? All right, so it's not really doing the right thing here. I don't know quite why. Did I interrupt it? Let's see, words encode. Yeah, I just think it takes a while. So let's do it again. We'll give it a while. Anyway, the point being, you're probably assuming at this point, and you would not be wrong to assume that this is performing the English language encoding of that file joff.bin, right? So eventually we'll get to the point where it will show you the encoded stuff. Now, while that's working, I'm not going to make you wait. I'm just going to open up another shellcode window and go here and show you the pre-encoded examples. So here I've got notepad x64 encoded.py. And if I look at this file, in fact, I'll use more instead of VI, you can see that we have a dictionary in Python here. There's an English word, and then there's a number. Well, that is the byte that corresponds to that word, okay? And it'll go all the way up to 255. So overfruited corresponds to the word 89, right? And so on. So now let's look at our shellcode 1 execution. Eventually, I'll get that right, right? In this script, I am very simply importing the shellcode from the shellcode file, okay? And then I am testing the architecture. If it's 64-bit or if it's 32-bit, I am setting a shellcode variable to that. And then I just display a menu to show what shellcode execution method would you like? Would you like to virtual alloc create thread in same process, or would you like to inject into a remote process? And you enter the selection, and down here, all in this code, and you can look at this for yourself because I'm going to give you the repo, it actually shows you exactly how the two different process injection methods work. And it's exactly the same that's in my slides, right? So let's run it, PyShellcode 1, okay? Remember, this is Notepad shellcode. So we're in a Python program we're going to hit number 1. I want virtual alloc create thread in same process. Oh, look, there's a notepad. It works, right? We have successful shellcode execution. I also want to point out something else. Somewhere down here, Windows Defender is running. Here it is. All right, here's Windows Defender. Yeah, I just created a clone of this machine, right? But Windows Defender, I mean, it's up and running. It's not disabled or anything, right? I mean, it doesn't seem to care. And that's using XOR encryption. Now we'll do this again and we'll inject into a remote process. Oh, look, shellcode execution. There's another notepad. Well, that's pretty. Okay, cool. Now, what I did there was I injected into servicehost.exe for PID 4428 and cranked off a thread, all from a Python interpreter, right? So that's the first version of the program. The second version of the program, Shellcode Execution 2, it uses, boy, I tell you, one day I'm going to get that right. It uses English language-based decoding of the shellcode. So we have to import from our modules here a lot more stuff. We need the encoded shellcode, but we also need the dictionary to decode it as well. And we've got that for both architectures at the top of the script here, all right? So let's run that script. And again, we're using these notepad files, which have already been pre-encrypted and pre-encoded for the purposes of this exercise. All right, here we go. Very similar menu. Let's go. Virtual alloc create. Oh, look, a notepad. We've got notepads falling from the sky, all right? And that used the English word decoding method, right? And create remote thread, same thing. Oh, look, a notepad, right? All this stuff works beautifully, just like you'd expect. And, you know, if you look at that notepad encoded file, boy, that's that doesn't look like shellcode, does it? Nope, doesn't look like shellcode, not one bit. But it sure does work as shellcode. And so you could choose to basically put your own shellcode in these programs if you wanted to. Okay, so let's go back and share screen again for the presentation, just to finish out for fun and giggles. All right. All right, so thanks for attending today. We're right up on 12:49 Eastern time in the US. You can find me on Twitter as I'm at Joff Thyer. I'd love you to follow me. I'm on Mastodon. I rarely check it, I have to admit. I'm guilty of rarely checking it. At Jedi Yoda at mastodon.social. And because I'm a giving guy, I'm really a generous type, I provided you with this repo of code that you can download and experiment with. And I would love it if you would do that. Thank you again for coming to see me at the Python Shellcode Redux, Webcast, Anti-cast, whatever we're calling it. And enroll in my Python course where we do lots of cool things like this. I would love to see you there. All right, Zach.
Hello. It was fantastic, man. Thank you so much for your time. Appreciate
Absolutely.
that. Didn't see too many questions come through. I don't know if anybody else grabbed any, but I'll look again through our teams. There's a couple there. You want to take a few questions, sir?
Yeah, sure.
Awesome. And just so everybody knows, we're going to spend probably the next 10 minutes here asking or answering questions that you guys might have for Joff. If you guys have any questions about any training or anything from Antisyphon, want to ask our team any questions, you can join us in the breakout room. So at the bottom of our Zoom screen, in about 10 minutes, if you click on the breakout room there, you can join Brian Strand. Kyle Ambrose will be there. I'll come in there in a little bit, and then you can ask any questions you might have about training and things like that. But for right now, next 10 minutes, if you all have any questions for Joff, please throw them in the chat and we will get to them as soon as we can.
I've got one quick statement. Just so for those that might be disbelievers, I have had pen testers in the company come to me and say, I got a Python interpreter, what should I do? And I've literally handed them very similar code, somewhat more obfuscated, but very similar code. And they have used it, succeeded, etc. So it's this is for reals, as they say, stuff that's actually been used in open engagements. So
I'm not sure if you answered this in the webcast or not, but in the Zoom Q&A, it says, does the Python version matter? Is there a good reason to stay on 3.9 rather than upgrade to the latest?
So that's a very, very good question. And the only, there's no specific requirements of third-party packages in the actual shellcode execution scripts, make sure I'm not lying on this, that go outside of, hang on, let me just double check that go outside of the pre-installed Python interpreter. So to answer that question, if you go with just purely Python 3.9 instead of 3.12, you're going to be just fine. And actually, I did have one addendum to that. There was the ps-util module that is required for remote process injection. That's a third-party package, but you don't have to do remote process injection. So you could edit the script to remove that single third-party dependency if you needed to do that, because you don't want to go around installing extra packages if you're in that pen testing scenario, right?
There's another question. What's your go-to tools for developing shellcode?
My go-to tool for developing shellcode itself is a C compiler, usually, sorry, having a brain fart. Usually Visual Studio is fine. And a lot of flags that I set inside of Visual Studio to turn off code optimization, stuff like that. And then you can actually copy from the Visual Studio debugger your shellcode directly out of there, or use things like nasm and disasm to command line disassemble object files as well.
Joff, another question that was in there. Can we get this image for this demo VM?
Yeah, no, you cannot, and you really don't need it. I'll tell you why. This demo VM that I put together is just a Python interpreter, and then it's got the repo of the Python scripts copied onto it. There's nothing special about this virtual machine. Truly, nothing special about this virtual machine. Grab a Python interpreter on a Windows box and download the repo, and you can replicate it very, very easily.
Does your class goes deeper into this subject, correct?
The class goes much deeper into the subject of introductory Python and learning the Python programming language. And then on the last day goes into some more advanced topics, and some of the shellcode execution samples that I've showed you are included as bonus material on that last day as well.
Saw another question about.
But now they're due for update because some of this stuff's better than that stuff. But anyway, that's all. That's life of an instructor. But anyway.
What happens with Defender if you run a real shellcode?
Try it. Frankly, the answer to that is it depends, right? If you so Defender has the ability to look at heuristics and network traffic as well, and Defender does have some logic in it that looks at network stack use immediately after process startup, and so you do have to be a little bit careful there. Let's say, for example, you use generic Metasploit with the defaults on a reverse HTTPS connection. Defender's going to catch you, right? Not because of the shellcode execution, but because of the actual behavior of the shellcode as it's executing that initial staged payload, right? So there's a more complex topic, and it depends is truly the only answer I can give you. What's my favorite shellcode I've ever made? I'm seeing that one there. Yeah, I don't think I can say. But custom shellcode that is not necessarily C2 focused, maybe shellcode that does things like reconnaissance on machines or things like that. Something a little bit more interesting than just purely C2. People tend to get really carried away with the idea that as pen testers, we always need command channels out of the environment. Well, what that means is the defense industry has gotten hyper-focused on trying to catch command channels out of the environment. So don't do that. Do something else, right? And so you'll find us and many others, if we're thinking about it, doing something else, right?
Does the shellcode execution only work on Windows operating system?
For the script samples that I gave you, that is the truth. They are focused on the Windows operating system. There are techniques to do so in Linux as well. I just don't have an example handy. So.
What EDRs have you used this against?
CrowdStrike, Falcon, Sentinel-1. I don't know, various. You know, they can potentially catch it still. There's no guarantees, right? You know, everybody wants you to say, I've got the magic bullet to get around all the things. No, this is not an easy thing anymore, right? I mean, these guys are training sophisticated AI models. They're looking very closely at net traffic behavior. They're watching the event tracing for Windows notifications carefully. They're looking at the kernel notifications carefully. This is a much more sophisticated challenge than it used to be. So I'm not going to give you a guaranteed this is going to work. This can give you a leg up. And if you get creative, you can get a little further than that. But there's only so much I'm going to share too. So,
do you have any idea why? Oh wait, it went away. Virus total flags a malicious Python file as Java.
That's I have no idea. That's
Okay.
a very specific question. That's unusual.
Okay. Just curious to know if there's any possibility to create a malware as .ics so it gets executed in the Windows environment.
Not sure I understand what that question was. Again, maybe I don't see it. Let me.
It's in Zoom, so I'm trying to grab the Zoom ones.
Just a reminder, we'll be ending here in a couple minutes. So if you still have questions for Joff, go ahead and throw them in the chat. We'll try to get as many as we can. If you all have questions for the Antisyphon team regarding training or career questions, certification questions, anything related to IT, cybersecurity, you can join us in the breakout room and we are happy to help you there. And that is only going to be for questions related to Antisyphon training. If you have questions for Joff, we will not be able to help you in that breakout room because we are not as smart as he is.
Oh, we're looking for calendar invites.
Calendar invites.
I don't have a specific ICS technique that I've got for you on hand right now. I mean, sure, it's possible. There's a lot of things that are possible. So you know, I think the general takeaway here is, you know, get creative when you're on your tests, right? If you go back to your same old tricks with it, maybe that's dropping a DLL or dropping an XE, and you know, that stuff's not going to work as well these days, right? There's a lot of stuff you can do in C# as well, but frankly, C# and .NET are very, very well instrumented now, and are getting caught a lot because the managed environment with the common language runtime interpreter is very noisy and very easy to see what's going on. So, you know, it's a tough area, right? And I know everybody wants the magic bullet, like, can we get around this? But I want you to be a little bit more objective and zoom out and think about it, right? Our job as security practitioners is to get us to a place where things are better defended overall, even though a lot of you might be pen testers and you don't like the fact that it's getting more difficult. The fact that it's getting more difficult means we're doing the right things as an industry. And that's
Joff,
a good thing.
on that one, Joff, there's a question. How could the blue team detect this or forensically find it afterward?
So, script artifact, clearly is going to be there. If you're running things like Sysmon, and I know a lot of people in managed SOC organizations and in large enterprises, they do like the granularity of Sysmon in environments on individuals with a well-tuned configuration. You would catch it in forensic event logging, basically the Sysmon event logging, where you're getting very detailed process execution information, and do a really, really good job of that. And of course, there's somebody just reminded me, there's also the PowerShell logging, which is maybe not so applicable to a Python process, but PowerShell logging is always a good thing to enable anyway. And it's very granular as well. But Sysmon is huge. I can't say enough good things about Sysmon. Go check it out if you haven't heard of it. It's part of the sysinternal suite of things, and it's a really great tool, and there's some good configurations out there, and you can get some really good data out of it. And you need to centralize your logging sources and be analyzing that stuff, right?
I'm going to head to the AMA room. We're 3 minutes past now. I'll let you guys keep
All right.
asking Joff questions.
See
but I'm
you
gonna
guys
go-
over there.
Joff, do you have more time, or do you need to get to another meeting?
I
or
probably should run,
Okay.
but listen,
Okay.
thank you everybody for attending. One of the things I like to say is that teaching is one of my passions and something that I really believe I have a skill at doing. If I didn't, I wouldn't be doing it. And I really do enjoy speaking publicly about these things and trying to help the community. And I'll be doing more of it. So I'd love it.
Awesome.
Come to my class. That would be awesome. And with that, I guess we can.
Yeah, no, absolutely. Thank you. Yeah, thank you, Joff, for doing this. We appreciate you. For everybody who's still here, if y'all have questions for the Antisyphon team, you can join us in the breakout room. Otherwise, I hope you all join us next week. We're going to have Andrew Krug here for AWS Cloud DevSecOps Essentials. So join us here, same time, same place next week. And thank you again for joining us. Thank you, Joff, so much. And again, join us in the breakout room if you have questions. We'll see you
All right.
all.
Bye. Bye,
Cheers, everybody.
Joff.
Good to see
Thank
you.
you.